lapel.
Learning her principles of biochemistry. Chapter 2, Water, the Solvent of Life. Weak interactions in aqueous systems, Part 1. Hydrogen bonding gives water its unusual properties. Hey there, welcome back to our channel. Today, we're diving into the fascinating world of chemistry and biology to explore the unique properties of water, specifically focusing on hydrogen bonding. So, what exactly is hydrogen bonding? Well, it's a special type of intermolecular force that occurs between a hydrogen atom and an electronegative atom, like oxygen or nitrogen, in a different molecule. In the case of water, hydrogen bonds form between the hydrogen atoms and the oxygen atoms in neighboring water molecules. You see, the oxygen atom in a water molecule has a slight negative charge, while the hydrogen atoms have a slight positive charge. This uneven distribution of charge creates a polar molecule, making water an excellent solvent for a wide range of substances. Now, what makes hydrogen bonds so special is their directionality. When the hydrogen atom and the two atoms that share it are in a straight line, the hydrogen bond is strongest. This arrangement puts the positive charge of the hydrogen ion directly between the two partial negative charges, creating a very stable interaction. These hydrogen bonds are not just important for water itself, but they also play a crucial role in the behavior of other molecules. For example, uncharged but polar biomolecules like sugars dissolve readily in water because of the stabilizing effect of hydrogen bonds between the hydroxyl groups or carbonyl oxygen of the sugar and the polar water molecules. One of the most fascinating effects of hydrogen bonding is its impact on the freezing and melting points of water. When water freezes, the hydrogen bonds lock the molecules into a specific arrangement, creating the beautiful crystalline structure of ice. Similarly, when water boils, the hydrogen bonds need to be broken, requiring a significant amount of energy. This is why water has a higher boiling point compared to other similar-sized molecules. Another incredible property of hydrogen bonding is its role in the cohesion of water molecules. The extended networks of hydrogen-bonded water molecules create bridges between solutes, allowing larger molecules to interact with each other over distances without physically touching. But perhaps the most remarkable role of hydrogen bonding is in shaping the three-dimensional structures of biological molecules like proteins and nucleic acids. These molecules have many intramolecular hydrogen bonds, which confer precise and stable structures essential for their functions. So, there you have it. Hydrogen bonding is the unsung hero behind many of the unusual properties of water and its significance in the world of biology and chemistry. It's incredible to think that something as simple as the bonding between hydrogen and oxygen atoms can have such a profound impact on the world around us. Water forms hydrogen bonds with polar solutes. Ever wondered why water is so special and essential for life? Well, it's all about those hydrogen bonds. Let's dive in and explore how water forms hydrogen bonds with polar solutes. Water molecules are like tiny magnets, with a slightly negative charge near the oxygen atom and a slightly positive charge near the hydrogen atoms. This polarity allows water to readily form hydrogen bonds with other electronegative atoms, like oxygen or nitrogen, in different molecules. When a water molecule interacts with a polar solute, such as a sugar or a hydroxyl group, hydrogen bonds are formed between the water molecule and the solute. These hydrogen bonds are relatively weak, but when many of them come together, they create a stabilizing effect on the solute, allowing it to dissolve in water. This is why alcohols, aldehydes, ketones, and other compounds containing polar bonds tend to be soluble in water. The hydrogen bonds between water and these polar solutes play a key role in their solubility. Water interacts electrostatically with charged solutes. Let's talk about water. You might already know that water is a polar molecule, which means it has a slightly positive charge at one end and a slightly negative charge at the other. This unique property allows water to interact electrostatically with charged solutes. When a solute carries a positive charge, water molecules surround it by orienting their negative ends towards the solute. This forms a hydration shell, effectively shielding the positive charge and stabilizing the solute in the aqueous environment. Conversely, when a solute carries a negative charge, water molecules arrange themselves with their positive ends facing the solute. This creates another hydration shell, preventing the solute from clumping together and keeping it dispersed in the solution. This process of water surrounding and stabilizing charged solutes is known as solvation. It's like water giving these charged solutes a cozy, protective hug to keep them from getting too close to each other. These electrostatic interactions between water and charged solutes are crucial in biological systems. They play a significant role in the structure and function of biomolecules, as well as in various physiological processes. And there you have it. Water's electrostatic interactions with charged solutes are a fundamental aspect of its behavior in solution. Nonpolar gases are poorly soluble in water. Let's talk about nonpolar gases like nitrogen, oxygen, and carbon dioxide. These gases are nonpolar, meaning their electrons are shared equally by both atoms, or the dipoles cancel each other out. Now, when these nonpolar gas molecules come into contact with water, something interesting happens. You see, water is a polar solvent, which means it readily dissolves charged or polar compounds but struggles with nonpolar substances. The nonpolar nature of these gases and the decrease in entropy when they enter the solution make them very poorly soluble in water. This is because water molecules are highly ordered around nonpolar solutes, reducing the entropy of the system. This phenomenon is known as the hydrophobic effect. Essentially, the nonpolar gas molecules disrupt the hydrogen bonding among water molecules, leading to a decrease in entropy and making them resistant to dissolving in water. Additionally, nonpolar gases interact with water through weak van der Waals interactions, which are weak attractions between uncharged atoms. These interactions further contribute to the poor solubility of nonpolar gases in water. And there you have it. The unique properties of nonpolar gases and water interactions shed light on why these gases are poorly soluble in water. Thanks for joining us on this chemistry adventure. Don't forget to watch the second part. Hit the like button and subscribe for more exciting explorations into the world of science. See you in the next video.
Pharma Pal.